Look at these two identical analytics dashboards. Both are tasked with finding the best 3-day sales streak. One crashes under the weight of the data, while the other updates instantly. The difference here has nothing to do with processing power. The frozen dashboard is relying on a naive, brute force algorithm. Redundant calculations have saturated the system, creating a software crisis that no amount of hardware power can outrun. To find a 3-day streak, a brute force approach groups days 1, 2, and 3. Then it drops that calculation entirely, moves one step over, and computes days 2, 3, and 4 completely from scratch. Notice what happened in the middle. The system just recalculated days 2 and 3, repeating work it had already finished a fraction of a second ago. On a short timeline, that's a minor delay. But scale this up to years of data, and the redundant work multiplies exponentially, creating a massive processing bottleneck known in computer science as the O of n squared trap. To rescue our software, we have to extract the correct answer without repeating the overlapping work. That brings us back to the instant dashboard. The algorithm already knows the total sum for the first 3 days. It doesn't need to add everything up again. It takes that total, subtracts day 1, and adds day 4. This diagram illustrates the sliding window technique. We start with a fixed boundary framing the first data points. To move forward, the window slides one position to the right. It drops the leftmost number outside the frame and pulls in the new rightmost number. A variable window applies the exact same logic, but its size adapts. It stretches to the right until it meets a specific condition, and then shrinks from the left if it violates that rule. Because every data point enters the window exactly once and leaves exactly once, the processing time drops to linear time, or O of n. But suppose our dashboard needs to find a combination of 2 specific sales days that hit a target, and those days are not next to each other. A sliding window always requires contiguous data to function. Once we look for scattered points, the protective frame shatters. Without contiguity, we need a different mathematical tool to parse the data efficiently. The solution starts with sorting the dataset, organizing it from lowest to highest to create predictable mathematical rules. Now we can deploy a technique called 2 pointers. We place a blue marker on the smallest value on the left and a red marker on the largest value on the right. We check their combined sum. If the total is too large, we step the right marker left, moving to a smaller number. If the sum is too small, we step the left marker right, increasing our total. Because the data is sorted, we can make a deterministic choice. If our current sum is too high, pairing that large value with any other number in our set will also exceed the target. By moving the pointer, we safely discard that number and prune every impossible combination it could have formed. Knowing which optimization tool to use comes down to one simple question up front. Do these elements need to be adjacent? If the answer is yes, you use a sliding window. If the answer is no, you sort the data and use 2 pointers. Both techniques serve the same master goal, transforming sluggish O of n squared bottlenecks into streamlined linear time.